Hello friends. In the previous lectures, we have been looking into different numerical operators. When we began the discussion about these different numerical operators, we began this discussion in the context of fixed laws. So fixed first law, it helps us understand, it introduced us within the context of the physical methodology, it introduced us to the numerical operator called gradient. So when you consider what this gradient involves, the gradient, it talks about the variation of a given variable or the change in a given variable with respect to the different axes that define our space. So in the context of fixed first law, or when we consider the fixed first law, the parameter that we are talking about is concentration, and we want to know how these concentration changes with respect to x, y and z, and that is exactly what the gradient helps us quantify. However, one feature of this gradient is, when you consider what the gradient operator is, each of these, the change of this concentration with respect to x, y and z, it is coupled with a unit vector. So therefore what ultimately we would have is the skeletal form of the gradient, or the nabla that helps us represent the gradient. The skeletal form of it will be of this form, wherein we have I vector coupled to the partial derivative with respect to x axis, j vector that is coupled to the partial derivative with respect to y axis, and k vector which is coupled to the partial derivative with respect to z axis. Now essentially then, when we consider the gradient of a scalar parameter, a scalar variable, then ultimately we would end up with a vector. So gradient of a scalar parameter will yield as a vector. Now in addition to the gradient, we saw this when we moved away from the fixed first law to that of the second law, we moved into a different operator called divergence. Now divergence, even though the skeletal form of the divergence is similar to that of the gradient, it's the nabla operator, it remains the same. What in divergence we do is we consider the dot product of two vectors. So we consider the dot product of another vector with respect to this nabla. So the nabla essentially, or the divergence essentially, considers the dot product of the skeletal form. So what we mean by the dot products of the skeletal form, so when we consider it, rather involves the dot product of this nabla, so when we have to then include another vector, so it means we are considering the nabla and the dot product with respect to another vector. Now in case of the fixed second law, what essentially we have done is we have considered the other vector to be the output of the fixed first law, that is the flux. So we have the combination of the nabla, the skeletal operator, that is a vector in itself, or the skeletal form of a vector, and with that we are including the flux, that is a vector that arises from the gradient of our concentration. So this is what we have considered in the fixed, this is what describes the fixed second law, of course with a negative that is involved in the convention. So ultimately, since we are considering the dot product, the divergence, the output of a divergence is a scalar. Now finally, to have a completion, we introduce another numerical operator which again considers the product between the nabla and another vector, but here instead of considering the dot product, the curl, it considers the cross product between the nabla and another vector. So we have the cross product between the nabla operator and a vector, that is we refer to as the divergence, and the output is a scalar. In case of curl, what we essentially have is a cross product between the nabla operator and that of another vector, and since it's a cross product, we end up having a vector. Now when we considered the cross product of two vectors, we saw that this can be expressed as the divergence of the matrix that is built. So essentially the direction associated with the cross product, the direction along which the vector that is the outcome of a cross product, the same is applicable to the curl as well, and then any geometrical association or the geometrical interpretation of the determinant that leads us to the cross product can also be applied for the curl as well. So what essentially we have done is we have looked into gradient, divergence and curl. So while the gradient it yields as a vector, the divergence it yields as a scalar, and the curl it also yields as a vector. Now the reason we need to ponder more on the scalar, or the representation of a given mathematical or a given quantity in terms of a vector, we need to dwell more on this is because it helps us rather describe a given material behavior in a more quantitative manner, in a more efficient way, in a more comprehensive way. Supposing we have, like the example we have considered earlier, suppose we have a precipitate, and this precipitate grows and transforms into an ellipse. So this precipitate grows and it transforms into, so originally this precipitate was of this form, and now it has gone and transformed into itself, or it has transformed into an ellipse. Now one way of describing it is the precipitate has grown and it has assumed the shape of an ellipse. So that will be rather a qualitative way of describing it. Now when we consider the flux that is rather responsible for the movement of the concentration, the propagation of the concentration, due to which we have the code of this phase, then based on the vectorial representation of the flux, we will be able to rather more convincingly describe the change in the morphology of the precipitate as it grows. So when we consider the concentration transport, when we consider the change or the transportation of the concentration, when we consider the concentration evolution using the vector representation like that of the flux, then we will be able to rather convincingly describe the shape that is assumed by the precipitate as it grows. So therefore, when we want to convincingly describe, when we want to rather comprehensively present the phase transformation and the shape assumed during the phase transformation, then we need to have, or we need to involve the vectorial representation of the concentration evolution. The vectorial representation of the flux, the vectorial representation of the concentration evolution will help us in describing, in understanding how the morphology of the given precipitate has changed as it evolves. So this is one of a rather simplistic example that we can think of. The other example is, if you consider the deformation in metals and alloys, crystalline material as a whole. So when we consider such crystalline material, the characteristic features of the crystalline material, which includes metals and alloys, is that the atoms have their positions, they have a long range regular arrangement of the atoms. So it means there are specific planes and directions that we are able to describe within a material, within a crystalline material. Now, when we impose a given stress, when we impose a stress, what essentially happens is the stress is experienced by the plane and also in the directions. So what we have is, in a crystalline material, because the atoms exhibit a long range arrangement, the way the atoms are arranged, they vary in a given plane and also a given direction. And when we impose a given or a stress on a crystalline material, the stress experienced by the material would also vary on a given plane in a specific direction. So therefore, we need to express this quantity, this stress, in such a way that we are able to differentiate the stress acting on a plane and a direction from that of another plane and another direction. So therefore, in such cases, for such quantitative description for a real life crystalline material, we need to have a representation that is similar to that of the vectorial representation. It is rather an advanced form of the vectorial representation, but nevertheless, we need to have not just a scalar representation but a vectorial representation. So both, when you consider holistically, so both in case of physical metallurgy, when we are talking about phase transformation, to describe the phase transformation in a more comprehensive way, we need a vectorial representation. We need to know how in which direction does the flow of concentration is, in which direction is the flux pointed, and because in that direction will our phase transformation follow. So therefore, it will help us rather understand the phase transformation in a more comprehensive manner. In the same way, when we consider the mechanical behavior, the stress and the response offered by the material, the vectorial representation of it will help us gain or differentiate the behavior of one plane, or it will help us describe the stress experienced by one plane along a specific direction when compared to the other planes in the other directions. Now, when we consider the generalized representation of the stress, supposing of a vector, supposing we have a vector A, so this is a vector A, and we are considering the generalized representation of a vector. So generally this vector can be represented in terms of the combination of the magnitude and direction. So A1 I vector, B1 J vector, and C1 K vector. So when I have a vector A, this vector can be represented as a combination of magnitude and the direction, where A1, B1 and C1 they describe the magnitude, and the I, J, K they describe the direction. Now, when you consider, during the introductory lectures on the vectors, when we rather brushed up our understanding of the vectors, we consider these I, J, K as orthonormal bases, so they are perpendicular to one another. In addition to that, we were able to also implicitly assume that each of these orthonormal bases, they align themselves along the basis or along the direction of our coordinate system that we often use. So we often use the coordinate system of x, y and z. X, y and z. Now when we considered these unit vectors I, j and k, we assume that the I, j and k, they align themselves along these axes that describe our coordinate system. So the generalized representation of a vector that involves magnitude and the direction. So the magnitude is given by a1, b1 and c1, the direction given by these unit vectors. These unit vectors, there is an implicit assumption made with respect to these unit vectors. One, we assume that these vectors are of unit length. Secondly, the direction of these vectors are along the axis of our coordinate system. Now, when we say that these vectors are of unit length, there is no specific unit that we have associated it to. So supposing when I say that in this context, in the purely theoretical context, when I say what is the length of this unit vector I, we write it as 1, but we do not attribute any unit to it. We do not write it as 1 centimeter or 1 meter. We just assume that it is just a unit vector of length 1. But when we want to have such an expression, such a representation of the scalar in a real life, in a physical condition such as this, then it is rather important for us to attribute a unit to these vectors. So depending on the scale that we consider, this unit vector can be of a unit centimeter length or a unit meter length, or it can also be a unit kilometer length. Of course, in the scale of or in the materials, it can be unit meter, unit centimeter, or it can be unit micrometers as well. So even though in the theoretical discussion it is sufficient for us to say that this unit vectors, they have unit length, when we want to adapt this representation to the physical realm, we need to have a quantitative description of what the flux is and how we need to describe the flux. We need to attribute a unit to these unit vectors, and depending on the system that we are considering, the unit associated with it varies. Now, for example, if I represent a vector as 3i vector, 2j vector and 7k vector, and units of these or each of these unit vectors are of length 1 meter, then this vector we are representing it in this manner, and each of these are of 1 unit length. And when you consider the coordinate system, this coordinate system, we have to move along 3 meters along the x-axis, 2 meters along the j-axis and 7 meters along the k-axis to reach this point here, to represent this a vector. So again, what I am considering is, I am considering I, j and k vector. Those are unit vectors and of length 1 meter, and when I want to then have a vector, I have to move 3 meters along the x-axis, 2 meters along the y-axis and 7 meters along the z-axis. Now if my unit vectors, again they are unit vectors but they are of length 1 centimeter, then the way I describe, so this is for 1 meter when my unit vectors are of length 1 meters. Now when I have a system, a coordinate system, wherein still the I, j and k vectors, they remain the same, they are unit vectors, but now their length is not 1 meter but their length is 1 centimeter, then in order to represent the same vector, I need to move 300 units along the x direction, 200 units along the y direction and 700 centimeter along the k direction in order to describe the same vector. So what essentially we have arrived at is, when we consider the representation of the vectors using I, j and k unit vectors, then depending on the magnitude that is associated with, depending on the length scale that is associated with these unit vectors, the coefficient that is required to describe a given vector would vary. Now if I am considering the vector that is required for me to describe the vector A, the representation that is required, the magnitude that is required for me to describe vector A when I am dealing with a unit vector of length 1 meter, then as a column vector this can be represented as 2, 3, 2 and 7. So I am considering a basis, an orthonormal basis, and the magnitude of this unit vectors are 1 meter, then I would need these magnitudes to represent the vector A. So the vector A in the orthonormal basis of 1 meter length can be expressed in this manner. The same vector along when the same vector and the unit vector are also pointing at the same direction, only now the magnitude of the vector is not 1 meter but 1 centimeter, then I need the vectorial representation for me to describe the same vector A is of this form: 300, 200 and 700. So what essentially then we have arrived at is, in order to describe the same vector, in order to express the same vector, the expression for it varies depending on the magnitude that is associated, or depending on the length scale that we are considering the unit vector. Depending on the length scale we are handling the unit vectors. When the length scale of the unit vectors is in the range of meters, we have this representation for the A vector. When it is in the range of centimeter, we have the same A vector being represented in this manner. So significant difference is, we have arrived at, there is a significant difference of expressing the same vector when we are considering the different length scale. And now, instead of relating our unit vectors to the coordinate system here, if we use a different coordinate system, then again, even though if we are considering the same length scale but using a different coordinate system, then again the way of expressing the same vector would vary. So what essentially we have arrived at is, the same vector, the way we are representing the same vector can vary depending on the length scale that we consider, or the way we define the unit of this unit vectors, and the same way the coordinate system to which we attribute our unit vectors to. So in case of here, in this case, we have attributed our unit vectors to Cartesian coordinate system. Now when we move away from, for our convenience, when we move away from Cartesian coordinate system to that of, say for instance, a spherical coordinate system, then correspondingly the way we represent a given vector A in the spherical coordinate system, or using the unit vectors that are based on the spherical coordinate system, will be significantly different from our representation using the unit vectors that are based on that are related to that of the Cartesian coordinate system. So what essentially we have is, we have the same vector being described in a different manner, that are expressed in a different way depending on the length scale that we are considering, and again the coordinate system that we are considering. Now the reason this is relevant is because while we are handling microscopic changes, while we are handling the flux in the microscopic range, then we will be using the scale, the unit vector at that in that scale would be 1 micrometer of length. Now if you are considering the fluid flow, if you are having a molten fluid or a molten steel that is flowing during your continuous casting, then essentially in that range, in that scale, our unit vector would be 1 meter of length. So correspondingly, so when you want to relate these two, when you want to have a vector representation that includes also the microscopic scale and also the macroscopic scale, when we have such multi-scale modeling, then when we want to have such multi-scale treatment, what essentially then we have is, we are representing the same vector depending on the length scale that we are dealing with, using different representation, using different coordinates. In addition to that, when we are considering a different coordinate system, so when we move away from the coordinates, the Cartesian coordinate system, when we find that using a spherical coordinate system is much more straightforward to deal with the evolution of a given phase, then again the way we represent a given vector would significantly vary. The same vector, depending on the coordinates that we are considering, the coordinate system that we are considering would vary. So therefore, this is not an ideal way of representing a given vector. So once we make this implicit assumption of relating the vectors to a coordinate system, and relating and attributing the axis of that coordinate system to this unit vectors, then essentially what we are doing is, and also relating these to a specific length scale, then essentially what we are doing is, we are making the expression of a given vector subjective to that assumptions. So if you assume that these I, j and k are part of this Cartesian coordinates and each have this unit 1 meter of dimension, then the expression of a given vector using this assumption, in this assumption, will be rather bound to this assumption. And when we move away from this assumptions, then we have a different representation of this vector. So this is rather not an ideal way of representing a vector, wherein the vector representation depends on the coordinate system and the magnitude of our unit vectors. Again, the length scale of your unit vector. So we need to then arrive at a way of expressing the vector that is independent of the coordinate system, and also that treats the unit vector as the unit vector without attributing any length scale to it. So that is the goal towards which we will be going forward. So we want to express the vector in such a way that we want to have a generalized expression of a vector that is independent of the coordinate system that we consider, and that is also can be adapted for any length scale, because even in our methodological research we deal with several length scales, and that's the reason we have this multi-scale treatment. So we want to have a vectorial representation that is independent of our coordinate system and that can be adapted for any length scale. So in order to do that, let us revisit our understanding of, let us consider two different coordinate systems that we are familiar with, and we will try to relate those coordinate systems, and by relating these coordinate systems we will attempt to arrive at a way of expressing a given vector that is invariant, that does not depend on the coordinate system. So now when you consider this representation, the actual representation or the way we attributed the I, j and k vector, so we saw that those form the part of such coordinate system. So I would be along the x direction, and j would be along the y, and the k along the z direction, and these form the part of the Cartesian coordinate system. Now besides Cartesian coordinate system, so this is the three-dimensional representation of the Cartesian coordinate system, the variables associated with it are x, y and z. Now besides Cartesian coordinate system, we also have the spherical coordinate system. So the spherical coordinate system, the variables that are associated with the spherical coordinate system in the 3 dimension. So what we essentially mean is, in this case, we want to rather describe a point in the 3 dimension. When we use Cartesian coordinate system, we need 3 components x, y and z. In spherical coordinate system, we also need 3 components, but the 3 components that are required are theta and phi. So what essentially we have is 1 length scale component and 2 angular components. This length scale component is referred to as the radial coordinate, and these are referred to as the angular coordinate. So a given point in a space can be described using the Cartesian coordinate system, or it can also be described using the spherical coordinate system. And in addition to spherical coordinate system, we also have the cylindrical coordinate system. In the cylindrical coordinate system, what we essentially do is we replace one of the angular coordinates with another length scale coordinate. So essentially we have r, h and theta. So these are 2 length scale coordinates, and this is an angular coordinate. So we have Cartesian, we have spherical, we have cylindrical coordinate systems. Now let us try to relate the Cartesian and the spherical coordinate system in the 2-dimensional case. So in the 2-dimensional case, you have your Cartesian, that is rather, so any point in a 2-dimensional space using the Cartesian coordinate system can be represented by x and y. In case of the spherical coordinate system, when we rather limit ourselves to 2 dimension, this is referred to as the polar coordinate system, and the coordinates that we need are r and theta. Since we have been looking largely into the Cartesian coordinate system, let us see how we would describe a point in a 2-dimensional space using the polar coordinate system. So if we assume this is a point, and to describe this point using the polar coordinate system, we begin by considering an origin O, and what we essentially do is we try to estimate the length, we try to describe the length between this point, the origin, and our desired point. Now when we have this parameter alone, this r, this distance between the origin and our desired point alone, and when we want to describe a given point, particularly in a 2-dimensional space, a given point using the distance between the origin and the point, this point can be anywhere within a circle. So within the circular region, within the circumference of a circle. So when you consider this circle with the origin as the center, so this point could be anywhere. So within the circle, in the circumference of the circle, this point could be anywhere. To exactly describe a position, we consider how much this position is inclined, or how it is inclined with respect to an axis that goes through the origin, and this inclination of this point is rather given by the angular coordinate theta. So what we essentially have is two-dimensional space, using the polar coordinate system, we will be able to describe a given point using r and theta, where r describes the position of a point from the origin that we have considered. And when we have this r alone, this radial component alone, then, and if we consider a circle of this radius r, this point could lie on anywhere on the circumference of the circle. So we have a origin, we have a desired point, and all that we know is the distance between these 2 points. Then essentially the point can lie in any point, or it can be anywhere on the circumference of a circle that is of the radius r. Now, in order to ensure that we are talking about the specific point, we need to consider the inclination of this point with respect to an axis that passes through the origin, and that is how we quantify theta. Now we have a point that is described in terms of r and theta. Now when you consider the Cartesian coordinate, this point can be described in terms of x and y. This point A can also be described when we, instead of considering the origin and the inclination, when we consider x and y, the coordinates, Cartesian coordinates of x and y, the same point A can be expressed in terms of x and y. Now in order to establish a relation between r and theta and x and y, what essentially can be done is, it is possible for us to superimpose the Cartesian coordinate system onto the spherical coordinate system. So when you superimpose the Cartesian coordinate system with the origins coinciding with each other, then it is possible for us to relate the r and theta to that of the x and y, the Cartesian coordinates that are required for the coordinates that are required to describe the polar system and the Cartesian system respectively. Now in order to describe the point A using the Cartesian, we need to consider the amount of x, the magnitude along the x direction and the magnitude along the y direction. So this will be x and this will be y, and correspondingly this point here will be y. Now it is possible for us to rather relate, when you consider this right angle triangle that includes the origin, the point, and this point here, origin, the point that we are interested, and this point here. If we consider the right angle triangle, this right angle triangle, because essentially we are dropping a perpendicular, so if you consider this right angle triangle, it becomes rather possible for us to relate the r and theta to that of x and y. Now in this right angle theta, if you consider the cos of theta, it will be x by r, and therefore the x is nothing but r cos theta. The same way it is possible for us by considering sin theta to represent y as r sin theta. So what essentially we have done is, this expression, using this expression, we have treated x, one of the coordinates of the Cartesian system, as a function that is dependent on r and theta. So x is a function. So if we are fundamentally considering, we need to understand what this means, because this helps us relate one coordinate system to the other coordinate system. So what essentially we have considered is, we have considered the fundamental coordinate system. As a fundamental coordinate system, we have considered the polar coordinate system, and based on that we are building a Cartesian coordinate system. So the x component of the Cartesian coordinate system, it is dependent on r and theta. Again, all these would have been familiar to you. You would have been very much familiar with all these translations, but the way we read these functions is quite important, because this will help us reach our ultimate goal of describing a vector using the notations, using the bases, or using the unit vectors that are invariant. So we need to understand what this expression here means. So our fundamental coordinate is polar coordinate, and we are expressing the coordinates of the Cartesian using the polar coordinates. The same way we are doing this. Now it is not only possible for us to begin with the polar coordinate system and to arrive at the Cartesian coordinate, it is also possible for us to start with the Cartesian coordinates and move on to the polar coordinates. So when we have such a consideration, you begin with polar coordinate, and when you move to, or based on polar coordinate, when we move to Cartesian coordinates, then the Cartesian coordinates, these variables are functions. They are not independent variables, they are functions, because we begin with the coordinate system. So that is what we did here. Now it is also possible for us to go the other way around, to begin with the Cartesian coordinates, and then to express the coordinates of the polar system using the Cartesian coordinates. So what I mean by that is expressing r as a function of x and y. Now this we can do that by just considering these expressions here. So we can square x and y and sum it up together. So it will have r square cos square theta and r square sin square theta. And on the left hand side you will have your r square. So r would then be rather x square plus y square whole power 1 by 2. So here the fundamental or the independent variables are x and y, and we are arriving at a function r. So it means we started with the Cartesian coordinate system, and from there we are moving on to the polar coordinate system. Now in the same way, it is possible for us to have an expression theta that is dependent on x and y, and this we will be able to do by considering this expression we will be able to arrive by considering the ratio of y by x, meaning r sin theta by r cos theta. So r will get cancelled off and we will be left with tan theta, and theta would be tan inverse of y by x. So what now we have done is, in these two cases, what essentially we have done is, we have started off with the polar coordinate system, and from that we have moved on to that of the Cartesian coordinate system. We were started off with the polar coordinates, and then we were able to describe the Cartesian based on the polar coordinate system. Now here in this case, we have started off with the Cartesian coordinate system. The fundamental variables are the Cartesian coordinates, and from that we were able to rather move on to the polar coordinate systems. Now if in this expression, if I substitute my x for the x square, I substitute these terms. If I substitute this expression for my x square and this expression for my y square, then what essentially I would be able to do is, I would be able to recover this function here. Let me repeat. So we have r, which is a function of x and which is a function of y, and now the x in itself is a function of r and theta, and the y similarly is a function of r and theta. Then when I do that, when I substitute my x and y, when I express my x and y in terms of r and theta again, then I will be able to recover my r. So what essentially I have done is, so in this case, so when you consider this case, we started off, when you consider these two functions, we started off with the polar coordinate system, and then we all moved on to the Cartesian coordinate system. That is what these functions indicate. However, when you consider this function as a whole, this r function as a whole, here we started off with the Cartesian coordinates, and we are moving towards, and it is possible for us to describe the r coordinates using the Cartesian, and when we combine both these, we are able to recover r, which is an independent variable. So we are able to recover this r when we consider when we start off from polar, move to Cartesian, and when we go back to polar, then we are able to recover the r, the independent variable. So it might superficially look rather trivial, but it plays a key role when we want to relate these two coordinate systems. So again, the same can be extended for theta. Theta in itself is a function of x and y, but this function x and y are in turn a function of r and theta. So therefore, when I substitute my y and x, and when I write my y and x, so which is here, when I write my y and x in terms of theta and r, then I will be able to recover from this expression. I will be able to recover theta, which is again my independent variable. This is something that you have to think and wrap your head around it. So what essentially we have done is, we are able to recover from our independent variable by treating the function as a function of another function. So we are treating this as a function that is dependent on x and y, and these x and y are not independent variables, but they are functions that are dependent on r and theta. So what essentially we are able to do is, we are able to recover the independent variables from that of these functions. So what it means essentially is, we will look into it even further in the subsequent lectures. What essentially it means is, the polar coordinate system is an inverse of the Cartesian coordinate system. The Cartesian coordinate system and the polar coordinate system, they are inverse of one another. So one way of understanding what this inverse means, and where we are able to extract this inverse nature of, or where we are able to comprehend this inverse nature of these two coordinate system, is when we are able to express these two coordinate system in this way, when we are able to express the coordinate that describes a given system in terms of the independent variables, and these independent variables are in turn related to other set of independent variables attributed to the subsequent or the other coordinate system that we are considering, then if we are able to recover the independent variable, then it is possible for us to state that these two coordinate systems are inverse of each other. So what now we have established is, we have considered two coordinate systems, and in these two coordinate systems, by considering their relations with one another, we are able to at least state that these are rather inverse of one another. Now it is possible for us to comprehensively rather prove how these are inverse of one another, that is by considering the derivative of each of these functions with respect to one another, each of these relations with respect to one another. So we have these four relations, and it is possible for us to consider the derivative of this relation, and using the derivative of this relation we will be able to show that these functions or these coordinate systems are inverse of one another. So that is where we will build we will start our lecture with. Now again, the reason why we are trying to do this, why we are trying to relate these two, is because we want to arrive at a set of expression that is independent of the coordinate system. We want to describe our vectors in such a way that is independent of the coordinate system. We don't have to have different representation of only one vector depending on the coordinate system and the scale that we are dealing with. And in order to do that, what we have now done is, we have now considered two different coordinate systems in two dimensions. These coordinate systems are familiar to us. We have considered these two different coordinate systems, and we have expressed the coordinates of each of these systems with respect to the coordinates of the other system. So that is essentially what we have done here. So the Cartesian coordinate system is associated with x and y, and we have written it in terms of r and theta. The polar coordinate system is associated with r and theta. We have expressed in terms of x and y. Now what we have done is, when we substitute x and y, and we have expressed x and y in terms of r and theta, we will recover r, and that is the same, and that is what we have written it as an expression here. And when we look at it closely, when we consider it closely, what we are essentially able to do is, we are essentially able to recover the independent variable from the function of r. So here the r is a function, and here the r is an independent variable. So essentially, even when we start off with a function through another coordinate system, so even though initially the r, the coordinate of the polar system, is a function, through the Cartesian coordinate system we are able to arrive at, or we are able to recover the independent variable associated with the polar coordinate system. Even though initially the coordinate of the polar coordinate system is a function of x and y, now through the coordinates of the polar coordinate, through the coordinates of the polar coordinate system, we are able to recover or treat it as an independent variable. So what it essentially then means is, initially starting off with a function, ending up with the independent variable through the Cartesian coordinate system. So what it essentially means is, this operation is only possible when these two coordinate systems are inverse of one another. Start off with a function, end up with an independent variable through a specific coordinate system. In this case, we start off with a polar coordinate, end up with the independent variable of the polar coordinate through the Cartesian coordinate. So it means that the polar coordinates and the Cartesian coordinates are inverse of one another. So this inverse relation between the Cartesian and the polar coordinate is what we will see extensively in the subsequent lecture. So we will try to see how this inverse relation between the polar and the Cartesian coordinate can be convincingly addressed in the subsequent lecture. Goodbye.